we have a rock with a mass of 540 grams that is found to have an apparent mass of 342 grams when it's in water. We want to know what mass of water is being displaced here. Let's draw a diagram of what's going on here. Here's a free body diagram of my rock in the air. It has a mass times gravity. We observe the weight there, so its weight is equal to mass times gravity in a static situation. Now in the water, we have mass times gravity acting down, weight apparent acting up. But now the buoyant force is also acting up, and that's why our weight apparent is less, because our buoyant force is pushing upward. So if you think about like hanging this from a spring scale or putting this on a mass balance, however you're measuring this rock's mass, it's going to appear to weigh less in the water. In the static situation where it's just sitting there and not accelerating, we can say that the sums of the forces have to sum to zero. So let's apply Archimedes' principle to try and answer this question. Archimedes' principle says that the weight of the displaced fluid is equal to that buoyant force. We have from the free body diagram over here, the sums of the forces in the y direction give us that the weight apparent plus the buoyant force is equal to mass times gravity. We know everything here except the buoyant force, so we can plug in these values and find the buoyant force by subtracting the apparent weight to the other side. This gives us a buoyant force of 1.94 newtons. And by Archimedes' principle, that's equal to the weight of the displaced fluid. Now to find the mass of the displaced fluid, we just use weight is equal to mass times gravity. We know that weight, we know gravity, we divide by gravity, and we get the mass of the fluid as that weight of the displaced fluid divided by gravity, or 0.198 kilograms, which is 198 grams. So we're displacing 198 grams worth of water. Part B, what's the volume of the rock now? All right. If we're inside the water, then the volume of the fluid displaced is equal to the volume of the rock. And the volume of the fluid displaced is equal to the mass of the fluid displaced divided by density, because mass is density times volume. As I mentioned, we're underwater, so these two things are equal. We're fully underwater. If we were floating on the surface, this wouldn't be true, but we're underneath. So this volume of the fluid displaced is equal to the volume of the rock, and we can plug in the mass of the fluid, divide by the density of the fluid, and get that volume of the fluid displaced, which should equal the volume of the rock. Part C, what's the average density? Well, the density of the rock is the mass of the rock divided by the volume of the rock. The mass is 540, the volume's 198. We divide that, and we get 2.73 grams per cubic centimeter. Is that consistent with the value for granite? I'll leave that to you to find out. I will say, yes, it turns out that's pretty consistent with a density of granite. So this rock might be granite.